Good evening, everyone. Thanks for coming out to my talk tonight. So today I'm going to tell you about exoplanets and the search for habitable worlds. But before we get started, I want to start out with this picture. It's a real photograph of a galaxy. A galaxy is a collection of stars bound together. We believe that our sun is a star in a galaxy that looks similar to this. Our galaxy is called the Milky Way, and it has over 100 billion stars. In our universe, we think there are over 100 billion galaxies. So how many of you out there think that there's another planet like Earth out there? Well, you're a self-selected audience. But now, a harder question is, first of all, that red dot is supposed to signify approximately where our sun would be in our galaxy, the Milky Way. So the harder question is, where, with respect to that red dot, would we be able to find an Earth-like planet in the coming years and decades, a planet just like Earth? And I know that you're not working on this, so you won't have an answer, but I'm just trying to get you thinking actively for my talk. So if anyone wants to just make a guess, just call it out or just think about it for a minute. So where, with respect to that red dot, can we find planets that we can identify to be just like Earth? Outer rim. Okay, I hear a lot of different guesses, but it's a bit of a trick question. It's actually within that red circle. So to find a planet just like Earth is really, really hard to do. And that's part of what I'm going to be talking about today. So what I am going to talk about is I'm going to address the 4 questions I get asked most often. I get asked these questions over and over again by people just like you. In fact, by all kinds of people at any level, my scientific peers. I get asked them by just people I meet on the airplane or children. Any kind of person asks these questions over and over again. So we'll start with the first question. What could aliens see looking at Earth from afar? It's the next talk by Seth Shostak that's about aliens. But for today, we'll just pretend they're out there and they're not too far away, and that they have sophisticated space telescopes to look at our Earth. And the question is, what could they see? Well, what's really interesting is we can start out with a real movie of Earth. And this movie is taken by a spacecraft called the Epoxy spacecraft. Some of you may remember it if you're a space fan. From July 2005, it was called Deep Impact. And it dropped something that landed on a comet and then tried to look and see what bounced back. And that spacecraft was actually just going through space, doing nothing, orbiting the sun. And NASA put out a call to say, does anyone have an idea of what we could do with this? And so I'm part of a team that is using it to look at stars with exoplanets and also to look back at Earth to see what Earth might look like from far away. So I'm going to show you a real movie of Earth from 31 million miles. And I want you to look for a bright white spot that's supposed to show specular reflection off the ocean. And look how red the continents are in this particular color scheme. Now look how lucky we were. That's the moon going in front of Earth. So it's a real movie that we have of Earth. And the question is, what would it take for aliens to see this looking from far away? What would it take them in terms of resources? Well, it turns out to see a picture like this is at a resolution of about 300 kilometers, it would take about 50, that's 50 meter in diameter, telescopes in space all working together. So that's far beyond with what we're able to do, and this is something they'd have to have a lot more money than we do, money to spend on space telescopes. They'd have to be more technologically advanced. So that is something that's extremely challenging to do. But what's easier to do, which they may be doing if they're out there, is a picture like this, a pale blue dot. And this is a much more grainy picture, much harder for you to see what's going on, but that's how it would look with just one telescope in space, one big telescope in space. And you can see here Earth, a pale blue dot. You can barely see it. It's less than 1 pixel. And this is also a real image. It's taken by the Voyager 1 spacecraft at 4 billion miles from Earth. And this is what I'm going to get to, what we hope to do in the future, is to see from not too far from Earth, looking far away, see a dot like this. But if there are aliens not too far away, and they have our capability, a little advanced, a little more money to spend, they could get a picture like this of us. Now this red band here is just scattered light in the camera optics. But you know what they could do if they could see this pale blue dot? They could actually learn a lot about our planet. They would see our planet vary in brightness with time, because you know how on a sunny day like today it's just so bright? Clouds are very bright. And if you're over the ocean's actually really dark. And so as the planet rotates, and the continents and clouds rotate in and out of view, the Earth changes in brightness. And we've actually shown with this epoxy data, with the planet just as a point source, that you can extract a lot of things about Earth. These aliens could learn that we had weather, which is indicative of liquid water oceans. They could infer that we had things like continents and oceans, and they could learn a whole lot of things. And what they really want to do, and what we aim to do for other planets, is to measure spectra. And I'm going to just introduce you to this concept for people who don't know what it is. But we want to take the light from the star and break it up. And you can think of this as like a rainbow. If you see a rainbow and could look very, very closely at a rainbow in the sky, you would see that there are dark lines, just like on this picture. And those dark lines are because of absorption from gases. And each line falls at a very, very specific color. So for example, on our own Earth, you've heard of carbon dioxide, greenhouse gas. You've heard of oxygen and ozone, the ozone hole. Those are the kinds of things that we're trying to see on planets far away by this method. And so if the aliens are looking back at us, they'll actually know that our planet has oxygen. And oxygen is a highly reactive gas. It should not be in the atmosphere at all in any significant quantities. And so they'll know that that's very unusual. We call that a biosignature gas, a gas that on Earth is produced only by life, by photosynthetic life, plants, bacteria. And it's actually in our atmosphere, 20% of our atmosphere by volume is made of oxygen. And at the risk of showing you, I just have one or two really technical slides here, just for people who know a little more science or engineering. I just wanted to show you this plot showing this is what a spectrum of Earth really looks like. This is wavelength in microns, and this is just brightness. But for the rest of you who don't understand spectra or this kind of plot, you just have to look at this and agree with me that this curve is very different from a straight line. It's very different from a straight line. And what's happening is you see these big features where those are like the dark lines in the rainbow, where light is being absorbed, and they're because of molecules. These ones are of water vapor, and all life on Earth needs liquid water. So finding water vapor in an atmosphere is a sign that there's liquid water. That's a great thing to find. But I'm just trying to convey to you that if aliens were looking at our pale blue dot from far away, and they could get a spectrum, get the rainbow with the dark lines, they could learn what's in our atmosphere. And if they knew basic chemistry, they would know that some things shouldn't be there. Water shouldn't be here unless we have liquid water oceans. Oxygen shouldn't be there unless we have some way to continually produce it, and we don't know of any way to continually produce it without life. So they could break things down, and I guess I can just say I hope they're out there doing that. So the answer to the first question, what would aliens see looking at Earth from afar? They would see a pale blue dot that varies with brightness, with time. And they'd see an atmosphere that has water vapor, oxygen, ozone, and carbon dioxide. The next question I get asked most often is, when will we find another Earth? On this question, I wish I could just give you an exact answer. We will find one in 1 day or 1 year or 10 years. But it turns out the story is a little more involved. And to tell you the story, I'm going to show you some more pictures. This one is an image of a planetary system. And what you're seeing here is a picture. The central part is, this is an image that's supposed to be a star. I'll get to this in a second. And you see 3 planets here. This one's kind of hard to see, but labeled B, C, and D, labeled in order of discovery. In astronomy, people aren't very imaginative. The names of planets are like 51 Peg. This one's HR 8799. Simply named whatever the star name is, and then you add a little B, C, or D in chronological order. So it's not even of order of distance from close to the star to far away. Gets a little confusing. But what you're seeing here is an image where the star has been removed. It's like trying to take a picture on a snowy day. I heard you get some snow here in winter. When you try to take a picture on a snowy day, this winter, I guess, was pretty rough. But on a snowy day, you try to take a picture, and what happens? Either the people in the image are completely dark, or it's just totally overexposed. And so that's the problem people have in trying to take a picture of an exoplanet. The star is so incredibly bright, you have to get rid of that starlight. It's like taking a picture in winter and having to get rid of the glare from the snow. And so by taking away the starlight, that's why the star looks so funny here. It's really taken away, and this is just what's left, trying to subtract it. But what's interesting, what's relevant for us today, actually, is what the state of the art is in taking pictures of exoplanets. So what you're seeing here is this particular planet here is 20 times the Earth-Sun distance. It's showing you the scale on the bottom. So if you wanted to find a planet like Earth, it would be 20 times closer in, like in here. It'd be hard to pick out compared to this noise that's left over. The other relevant thing is the brightness difference between that star that was there before it was removed from the image and the planet. In this case, it's a difference of about 1 part in 100,000. But our own Earth compared to the sun is about 1 part in 10 billion. And to understand that number a little better, I want to ask you, what can you buy in Kansas City for $1? Chocolate bar? Okay, you can buy, let's say, a chocolate bar. But just to understand how huge those different numbers are, is what could you get, I guess it wouldn't be limited to Kansas City, but for $10 billion. Such a huge difference. And so in astronomy, we're faced with this huge difference, that the sun is 10 billion times brighter than Earth. And so if we want to be able to take a picture of an Earth, and we're not talking about that beautiful picture we like the movie, we're talking about that pale blue dot, the point, we would need to actually get rid of that starlight. And that's a huge challenge. It's the biggest challenge we face in astronomy in the search for planets like Earth. And by the way, I forgot to say, if you have any questions related to the slides, ask them now. We'll have a small chance for more general questions at the end of the talk. And our host, Eric, has a microphone if you want to ask a talk, so it's all being recorded, so we can keep that on. But I want to tell you about one really cool development about how we're going to get rid of that light. And this goes back to some high school physics, basically. But what I'm showing you here is a circle. You can think of this like a telescope mirror for a telescope in space. And you know, if you take a telescope in space and take a picture of a star, you might think that you'll see just a dot in your image. But in fact, you don't see that. You know what you see? You end up seeing this. Instead of seeing a dot, you see like a blurred part in the middle, and then you see these rings. And you know, it doesn't look a lot like when you drop a pebble in the water. You get these ripples. And it's actually from light that goes around the edges of that circle. Think of that like the telescope mirror. Goes around it, and it actually diffracts. It's called diffraction. And this is a problem, because for planets like Earth, these rings, the first ring here, it's actually 100,000 times brighter than the planet you're looking for. So you could put a telescope in space, but the problem is you have this problem with light, and it interferes. And so one of the really exciting developments that isn't really talked about is how to get around that problem. And what people have thought of, I'm going to oversimplify this, so I hope everyone can try to understand it, is instead of having that big circle for your telescope mirror, you can have a different shape, like this. It's kind of like a cat's eye. We call it a Gaussian, cat's eye. And this is the image you would get. So instead of getting rings, you would get some locations of the image would be very, very dark, and the bright areas would be over here. And one of my friends actually took this idea and worked out mathematically how you could get the optimal, like, dark area. And then people came up with all these special shapes. Imagine if your mirror was shaped like this. Then look, you'd get a pattern of light like this. Dark areas here, and bright ones here, or dark like this. So it's a really nice idea, and people have actually demonstrated in the lab that this really works in the lab. And it's kind of a new movement in optics, and it's been motivated by the whole search for other planets like Earth. And by the way, it's not really the mirror that's going to be this shape. It's going to be a little piece of something cut out somewhere inside the telescope. Now, the problem with this idea is that you have to have an almost perfectly smooth telescope mirror. It has to be about 1,000 times smoother than a human hair. And it's basically impossible to make a mirror like that. You have to, even in space, little things happen, the telescope moves and the mirror gets distorted and things, and so you have to be able to actively control that mirror. And lab experiments have been done to show that you can reach this, at least on the ground. And you'll see where this is going. It sounds like it's really difficult, but as I go through my talk, I'm going from really hard to much easier to things that we're actually doing right now. And so people took this idea and did something even more radical, and it's an equally challenging idea, but I think it will sound even more difficult to you. And that is to take that special shape and put it outside of the telescope. So instead of having that somewhere inside the telescope, you could put that special shape outside. This is supposed to be the same shape as that star before. And now that this shape is outside the telescope, it blocks out the starlight so that only the planet light reaches the telescope. And the reason we're so excited about this particular idea is that your telescope doesn't have to be a perfect telescope. It can be a telescope like one apparently you heard about last year, the James Webb Space Telescope, which is supposed to launch in 2014. And you just have to figure out how to build, deploy, and do station keeping for this thing. And then you can do this. Now, the reason this thing got off the ground was there were two people who worked for an industrial aerospace company. And they were really excited about large deployables in space. The problem was they couldn't tell us why they were excited or had experience. because clearly they had some relationship with this with defense work. But they thought even though it was different from what they had originally done, they had motivation, they got their company to invest in it, and this is moving along right now. So this is how we want to find planets just like Earth, and I'm going to go over 2 more techniques now before I get back to the bigger picture. So we have easier ways to find Earth in this really complicated telescope in space, and this way is so-called the wobble method. This picture is trying to show you that the planet and star, well, the way that we describe this, which is actually wrong but easy to understand, is that the planet is tugging on the star. If the planet tugs on the star actually moves, and you can measure that movement of the star. We call it the wobble method. You see the star wobbling. What's really happening is the planet and star are orbiting their common center of mass. And you can see the star move, and you can infer that there's a planet there. And to find an Earth-mass planet, this actually is something people are trying to do right now, pushing down to planets as low mass as Earth. We have another way to find planets, and this way is called the transit method. And here's an artist's conception showing a star like our sun with the planet going in front of the star. And this happens. Some planets are lined up just so they go in front of the star as seen from Earth. You can tell it's an artist's conception because they thought the artist Lynette Cook thought it was too boring and added this nebulosity out here. Spruce it up a little. But in fact, as you know, we don't see any other stars like this. We can't see them all resolved. Instead, they're just point sources, and so what we really see, the picture we really have, it's not as pretty, but it's really a graph like this. This is time, and this is star brightness. So most of the time, the star is just constant in brightness. Except when the planet goes in front of the star, look at that. The star drops in brightness, just a little bit, by a few percent. And so in fact, that's something that's happening, and I wanted to tell you that almost a little more than a year ago, I made my first trip to Cape Canaveral, and I got to witness the launch of a very special space telescope. It's called the Kepler Space Telescope by NASA. And it was basically a perfect launch. It was a night launch, it went up, and I encourage you to go to Florida to see a launch, even if, the actual unofficial viewing sites are better than the official NASA viewing site. Because in the NASA one, you see it go away from you. You're near the rocket and you see it launch and go away from you. But if you're on the beach, you actually can see the spacecraft arch across the sky. You just have to coordinate your trip to Florida with the public knowledge of when the things are going to launch. And when you see it launch, the booster rockets, you can see them, they're really hot, and you can just see them like floating down like this. It was breathtaking. And the voice that does the countdown, they had loudspeakers out, and that voice was exactly like that voice in the movies. Now, this space telescope was actually conceived of a long time ago, about 25 years ago. And the person who's in the science PI, Bill Barucki, he's probably in his 70s now, but he was there, and it was an amazing experience. He was there, like 3 generations of his family were there. They had known he'd worked on this for so long, and lots of people, and after it launched so perfectly, people who had worked on the project for 15 or 20 years just said they didn't know whether to laugh or to cry, like to be so happy, because it went up there, it didn't break, it's there. And what Kepler's doing now is, it's really interesting, but it's looking at one very wide field of stars for 4 years, staring. And what it's trying to do is look at 150,000 stars. And it's looking for this picture, this little drop in brightness. Kepler is going to tell us how common are other Earths. Does every star have an Earth-sized planet in an orbit like Earth's? 1 out of 10, 1 out of 100? And when Kepler gets that number, it'll help us figure out what to do next. And I wish I could convey to you all the excitement on the team, but it's like looking for a needle in a haystack. I mean, you'd know how to do that, right? If someone gave you a haystack, you'd know how to find the needle, but it would just take a long time and a lot of tedious effort. And the needle in the haystack here is that you can find a lot of things that look like this kind of picture. A lot of things look like that aren't planets, and it takes a lot of effort to search around. So to finish this part of my talk, when will we find another Earth twin? Well, we'll know the frequency of Earths, how common are other Earths, in about 5 years when Kepler finishes its job. If we're really lucky, we could have a planet the mass of Earth within about 5 years by the so-called wobble method. But I want to tell all of you that Venus and Earth, the planet Venus and Earth, they basically look the same to these methods. Venus is about the same size as Earth, it's about the same mass as Earth, and so we won't be able to distinguish between Venus and Earth. For those of you that know about Venus, its surface is over 700 Kelvin, it's hot enough to melt lead. So in fact, they're very different when it comes to life, because life cannot survive on Venus. So that's why I went over that, despite how crazy or hard it was, the whole taking a picture of Earth with the fancy space telescope or the fancy external occulter that can block out starlight. That's why that's our ultimate goal in exoplanets. But I didn't come here to tell you about 25 years from now. So the next part of the talk is when we find another Earth part 2. And there is something exciting happening now. And it's really based on, it reminds me of the story, when the person drops her keys and looks under the searchlight, because that's the only place where she can find them. It's a little bit like that, and it basically involves being generous with the definition of Earth and allowing Earth to be something quite different from our own Earth. And I'll get to that in a minute. But to introduce this, I wanted to tell you a story from a few years ago when I was consulting for National Geographic. They had a really nice cover story article about the search for Earths. And here's one of the pictures they had. In fact, the analogy that we have for when we want to take that picture of Earth that's so hard to do, it's the analogy of searching for a firefly next to a searchlight. Only that firefly would be about 6 feet from the searchlight, and the searchlight would be 2,600 miles away. That's like the distance from New York to Los Angeles. It's very, very hard to do. The thing with National Geographic, they have great pictures, real photographers. They wanted to really take that picture. So they rented these searchlights. They went to some field, somewhere, probably in Maryland. The first thing I didn't like was you never see stars all clustered together. It was my job to comment on all the illustrations and photographs they had taken to see if they were really accurate or not. But in the end, they had to fake the firefly, because it's not 10 billion times fainter than the searchlight. But the most interesting thing about this was they actually came back super excited because they did take a picture. But the picture they took, or that they made, was actually of the firefly in front of the star, not beside it. The firefly in front of the star blocking out some of the starlight. And why I was so impressed was that these non-scientists, but great image makers, they figured out on their own that this is almost impossible to do. But the planet in front of a star, that transiting planet, is actually not so hard to do. And so the next part of the story about when we find another Earth part 2 is actually, and by the way, so for Earth, remember we said 1 part in 10 billion. The Earth is 1 part in 10 billion fainter than the sun. But if you want to look for the Earth going in front of the star, blocking out the starlight, that's only 1 part in 10,000. Still a very hard number, but much easier than 1 part in 10 billion. So the goal right now is to do something easier and to find a big Earth transiting a small star. And this is an artist's movie about showing the planet going in front of the star, just so you really understand what it is. We assume that in our galaxy, the orientation of stars is all random. There's no reason why they should have any preferred direction. So we can work out the probability to find planets that go in front of the star as seen from Earth. And the goal is to do this and to find a Goldilocks planet. Not too hot, not too cold, but just right. Just the right temperature for life. A planet that's too hot, atoms can't join together to form molecules to make the ingredients for life. A planet that's too cold won't have liquid water or liquids that life needs for chemical reactions to happen. So the goal is to find one that's just right. Not too big, not too small. We'll see what's out there. So we have a special name for this. We call it the M-star opportunity. And the idea is to look around a really small star. This is showing you a kind of schematic figure, showing you Earth and the sun. And actually, the probability for a transiting planet drops the further you are from the sun. Think of it like throwing darts at a dartboard. If you're really close, it's really easy to get that. Far away, it's a lot harder. Now, for Earth to transit the sun, the probability is 1 in 200, so you'd have to look at least 200 stars. And you'd have to look at those stars for a year. So in academia, we have a kind of joke because a life cycle is really 5 years. 5 years is how long it takes a PhD student to start and finish. But if you have to wait a year, you have to wait, first of all, to get your experiment running, and then you see something happen. Then you have to wait another year to happen again, and then another year to confirm it. You're basically waiting forever. And so the nice thing about planets that are really close to the star, based on Kepler's law, they go around much faster. So a planet close to the star, it's only going around every 13 days. And all of a sudden, that student now has a lot of events, a lot of chance to build up a signal. So there's many reasons why it's favorable to find a planet going in front of the star, close to the star. And what this is showing you here, these distances, are the so-called habitable zone or Goldilocks zone. Planets are heated from the outside from the sun. So the further away a planet is from the star, the colder it's going to be. And these small stars, they have a very low luminosity output. They don't give off a lot of energy. So their Goldilocks zone is much closer. That's what this is showing you here, much closer. And so it's a small star, it's closer, everything's in the favor. And one more thing that's in the favor is just the size of the signal. For Earth, it's 1 part in 10,000. For these close ones, 1 part in 1,000. So everything works in your favor, and there's a huge race now to find these planets. Now, it sounds great, and instead of showing you a complicated model, because I work on models of what the planet would look like and how we should find it, let me take you on a virtual trip to one of these planets. First thing, this is an artist's conception of one of these planets, and there's no planets we know of that are in the Goldilocks zone yet. We don't know of any, but this is the idea. If there were one, maybe it would look like this. And what the artist is showing us here is, first, look how big the sun is in the sky. The planet's so close to the sun, if we could go to that planet, we'd see a huge sun looming in the sky. And what else is really interesting is on this planet, the sun would always be in the same place in the sky at all times. Because the planet is so close to the star, it has this interesting property. It shows the same face to the star at all times, just like the moon does to Earth. So in fact, so I would ask you, which part of the planet would you live on? The part that's always daytime, or the part that's always nighttime? Some people like night. If you're an astronomer, you want to be on the night side. You could go somewhere where it's always setting. And if you're a child, the great thing is you could have your birthday. Every once that planet goes around the star, which in this case, remember from the example, was 13 days. So 1 year is only 13 days. So it sounds like a pretty interesting place to visit. This artist actually has shown you another transiting planet in the same system going in front of the sun. They're showing you another planet further away, and they're using their artist license to figure out the colors here. But the interesting thing about these planets around the small stars is they might not be such great places to go after all. The stars are very active. They give off a lot of radiation. So you might not be able to use your iPhone out there. Maybe a very dangerous place to live because you're going to get blasted by UV radiation. Other people who try to understand how planets form don't think it's such a great place, that some of the basic building blocks for life, for a variety of technical reasons, wouldn't be available where these planets form close to the star. So I could say that the jury is out on how great these places would be for life. But one thing everybody agrees on is that a big Earth around a small star is easy to find. And I want you to keep this in mind because anytime in the next, I don't know any secrets here, but anytime in the next months or year or two, you may be reading about one of these in the news, because when somebody finds the transiting planet, big Earth around a small star, it'll be big news. It'll be the first planet we have that we think could support life. And we're expecting that to happen anytime soon. When we find another Earth, part 2. A big Earth transiting a small star, anytime, but certainly I believe within 3 years. Now, before I move on to the next question, I'm going to risk just showing you one slide that might be too technical, but I wanted to convey something important. And this plot is showing you all those symbols, all the planets we know about. There's over 400, probably about 450 symbols on that plot. And what you can look at here are the different colors and the different shapes. Those are all different techniques used for finding planets. There's actually 6 different ways to find planets. 5 of them have been successful. And you can see on this plot here, it's actually showing you distance from the sun. So the sun would be here. Earth is 1 in the units of 1 away. And this is mass and Earth masses, so Earth is 1 Earth mass. And so what you're supposed to see from this figure is that planets exist at a variety of masses, anywhere from just a little more than 1 Earth mass up to almost 1,000 Earth masses. And planets actually have orbits from their star. Almost any orbit you can imagine is there. It's really amazing how diverse planets are. See here, the solar system, Mercury, Mars, Venus, Earth, Uranus, Neptune, Jupiter, Saturn. They all in this neat sort of line here, but none of these other systems look anything like our solar system. All planets, different masses, different areas. And it's safe to say that the dark parts of this diagram are dark only because technology can't reach there yet. Technology can't reach the low masses. It can't reach low masses far from the star. But I just want you to know that there are so many planets out there. They're so diverse. There's all kinds of planets. And here we're really only just scratching the surface. So when I talk about finding a planet that maybe will have life, may have liquid water, may support life, the next question I get is, can we go there? Everybody wants to explore. And so that's the question I get, the single question I actually get asked most often. And even if I talk about it in a talk, I still get asked it in the question period. So let's talk about distances. Here's a real picture of our sun taken by the SOHO spacecraft. We're going to use this as distances using the sun as a reference point, this particular image. Who wants to take a guess about how big Earth would be compared to this image of the sun? Someone guessed correctly, the sunspot. The small dot on the screen, that's a sunspot, the dark dot. And Earth would actually be about that size. So that's how big Earth would be. Now the question is, if this were the size of our sun, how far away would Earth be from the sun? Why don't you just raise your hand if you think you're about the same distance from the screen as Earth would be from that sun?
Sarah, we have a question too.
Okay, let me just finish this and then we'll get to the question.
Okay.
I don't see any hands, so does that mean you guys think it's somewhere else or somewhere else? Further? Omaha? Okay. Well, in fact, there's a nice number here that the Earth is about 100 suns away from the sun. So you can look at the sun and just kind of count to 100. So your guess is as good as mine. I don't think it's in this room, but it's not too far away. Okay, now the next question, before we get to your question back there, is how far is the next star if the sun is this size? And I'm not expecting you to know the answer in advance. We're just trying to convey distance here. Someone says New York. And actually, I'd have to do the math in my head because it's kind of tricky. So we're just going to roughly estimate here. It would be further than New York. It would probably be, since I'm not from the Midwest, it's hard for me to guess. You know how if you fly over the pole, it's a little different if you go to Europe? But it's probably something like, it's probably about 6,000, let me think. No, it's probably about 4,000 miles away. So where, can someone tell me where 4,000 miles would be? Where? Hawaii? Okay, Hawaii is a nice place to visit. Let's take Hawaii. So think about that. If our sun is this size and the next star is like in Hawaii, and that's the closest star. Most stars are much farther from that. This distance between stars is just so vast that going there is going to be challenging. Now, I'll get back to the story after we take this question.
You are ahead of my question, but the small stars, what's their duration of life compared to larger stars, even though probably they're not inhabitable by life? Is that a factor, the length of life of small stars?
Good question. So the question is, do small stars live long enough for life to develop? And in fact, small stars are the longest lived stars we know about. The bigger stars burn out faster. Sun's kind of in the middle. So they're even better than our sun because they live a very long time. So let's talk, now we have a sense of how vast things are. Let's talk about the nearest star, Alpha Centauri. It's about 4.2 light years away. 1 light year is about 6 trillion miles. So we're talking about 25 trillion miles away. Here's a picture of the Voyager spacecraft, Voyager 1. Remember the one that took the picture of Earth as that pale blue dot? Voyager 1 would, right now it's traveling at about 20 kilometers per second out into space. If it were pointed at Alpha Centauri, which it's not, it would take 70,000 years to get there. And that doesn't even include slowing down. So that's how hard it is to get places. Now that said, one of the callers in on the radio show this morning, you can listen to the show if you want to, you can go to the web and listen to it, but one of the callers got mad when I was talking about this because the caller, rightly so, I agreed with the caller. They just said, it's so limited, why are you so narrow-minded? And I even said, well, the example I gave was better than this though. I said there are some brave engineers who think that somehow, someday, we can travel at maybe 1/10 the speed of light. So if the nearest star is 4 years away, and we travel 1/10, that would take 4 times 10 or 40 years to get there, 40 years. And that's no longer so crazy, is it? I mean, it's sort of within a human lifetime. And I was in California a couple of weeks ago giving a similar talk at Caltech to some undergrads, and I said, age 20 is the best age. If we could do this and you're age 20, you could go in that spacecraft, maybe kind of go in a hibernation phase, and then 40 years later you could wake up and you'd be 60 years old, which is a good age. And then you could go there, and actually one young woman came up to me and said if this were possible, she would volunteer to do it. And another person beside her said, that's a one-way trip. Because, by the time she got back, she'd be another 40 years, 100. And she was serious, and it might sound funny, but, she just said it would be she'd be the first person to see another planet and, to go out into space. And I'm just trying to convey to you how excited people are about the idea of going to another planet. So I don't see this happening anytime soon, but I do know people are looking for Earths around Alpha Centauri, and I believe if they find one, people will figure out a way not to go there ourselves, but to send a probe there. Some people talk about you could launch something small, cell phone-like, and then as that goes further and our technology advances, you'd send another one, and then one would communicate back to the first one, and that could communicate to Earth, and so you don't have to do the big thing all at once, but start sending little things. And so we're only really limited by our imagination, and that would be my response to the caller. But the technical detail with the caller was the whole issue about the speed of light, because from Einstein's theory of relativity, nothing can travel faster than the speed of light. And so that's a problem, because then it would take 4 years to get to the nearest star. And the speaker wanted to know, why couldn't we go faster than the speed of light? Maybe other aliens can figure that out. And what I didn't get to say was, we have some fundamental laws of physics. And the one I used was gravity. I said, I bet nobody here would jump off a 30-story building because you believe in the law of gravity. And there's other laws we have other reasons to believe in. And we believe right now that nothing can go faster than the speed of light, but maybe in the future that'll change. That's why I agreed with the caller. Maybe someone will figure out there's really another set of laws that applies in some other way, and that would help a lot. But to summarize this part of the talk, can we go there? Not for now. It's the best question, the favorite question that I get asked most often. So then, the people who ask this question, they ask the follow-up question. If we can't go there, why look? Why are we looking for these planets? And this is because we can actually learn a lot of things remotely. This is about the 400-year history of astronomy with telescopes, starting from when Galileo first turned his telescope to the skies. Here's what we want to learn. We want to find signs of life. Now, next week, you're going to hear, if you come back, about aliens. In our case, we're not necessarily looking for aliens. We're just looking for some kind of gas that we think is produced by life in the atmosphere. And we actually wouldn't be able to know for sure if that was produced by bacteria, like that picture shown on the right, or if it was produced by complicated life. We may have ways of guessing, but we can't be sure what is producing it. We want to look at these planets, and we want to look for signs of life in the atmosphere that indicates that there could be life there. And that's why we're looking for these planets. Now what I want to do is I want to show you some real data for things we're doing right now. We're not looking at small rocky planets now, we're looking at big gas giants. We don't think any gas giant will have life, planets like Jupiter, because they have no surface as we know it. When you go into their atmosphere, deep inside, they get very hot very quickly, too hot for complicated molecules for life. But nevertheless, we have a lot of data and a lot of exciting things are happening right now. So here's a schematic showing you the planet going in front of the star and behind the star. And these are the planets that we have access to. They're the ones that are letting us take data on them. So I'm choosing a few highlights to show you. I'm showing you 6 pictures here of different planets going in front of their star. And remember before, this is actually time along the bottom, and this is just relative drop in brightness. And remember before we talked about the planet's constant in brightness, then the brightness drops, and then comes back up. But I'm showing you these just to show you all the a few different examples. And the people who take these data came from one of my colleagues at MIT, they would call this their family portrait. Because you see these are objects that people work on, and they're all a little different. And from these figures, you can actually, I worked out a theory that told you all the things you can learn. You can learn the size of the planet and the size of the star. You can learn a lot about the planet just from these particular images. And we have over 70 picture graphs like this telling us about planets that go in front of the star. And what we try to do with this information, we ultimately get a size of the planet. We can combine it with a mass. And we just try to understand what the planet is made of, on the inside. This is just showing you an artist's conception of Jupiter. It's a big planet made mostly of hydrogen and helium. We think it might have a heavy element core. And here's showing you 2 other examples, that a planet of the same mass, about 22 Earth masses, it could either be big like this and made of water and ice, or if it were a big 22 times the Earth's mass and made of rock, it would actually be much smaller. So there's kind of a very complicated theory and a lot of computer models that just says when we have a mass and a radius, we can tell you approximately what the planet is made of on the inside. And we have other exciting data about these hot Jupiters. Here's an artist's movie, again, showing you a planet going around the star, in front of the star, and behind the star. And these planets are so close to the star, we believe they're what we call tidally locked. Just like the moon, they show the same face to the star at all times, just like the moon does to Earth. And we have something really interesting here, because that means the planet has a permanent day side and a permanent night side. So my last question for you is, if the planet is heated only on one side and not the other, do you think this means the planet is super, super hot on one side and very, very cold on the other? Or do you think that winds make the planet the same temperature all around? I want to take a vote on this one. So do you think the planet, if it has a permanent day side and a permanent night side, is it really, really hot on one side and really cold on the other? Okay, most people say yes. Or do you think it's the same temperature all around? Yeah, I hear a couple of comments here saying if it has an atmosphere. And in fact, I love asking this question because if you were brave enough to put your hand up, then you were right. And yeah, okay, someone's got 2 hands. And we actually have real data on this stuff showing that what we think is happening is that actually some planets do really seem to be really hot on the one side and really cold on the other. And other planets seem to have a more even temperature all around. And this is where it gets a little complicated, but I'll just try to explain it in a kind of easy way, and that is, it depends where in the atmosphere the energy is absorbed. If the energy from the star is absorbed very high up, typically that energy will go right back out. But if the energy can penetrate very deeply into the planet, then it usually gets moved around rather quickly. And so there's a theory, it just depends on what's in the atmosphere, if there's a layer of things that in the atmosphere that's highly, highly absorptive high up. And we have growing evidence that there really is a range of things that are going on these planets. And let me see, I only have a couple of more slides here. One other this is getting a little technical, but it's one of my last slides, I wanted to show you real data from a planet atmosphere. And this was taken with the Hubble Space Telescope. Just think of this as strength of the signal, and this is wavelengths. This is in the what we call the near infrared, from about 1.4 to 2.4 microns. And what I want you to look at here are the black triangles. That's the real data from the Hubble Space Telescope. The curves are models. And again, you're supposed to agree with me that this is different from a straight line. You cannot draw a straight line through all those points. And that's because there's absorption from molecules here. And furthermore, you're supposed to ask which curve agrees with the data better. So say the red one agrees better because it goes through these points, and the blue model doesn't go through. And actually, sometimes people ask, what's all this stuff in the model here? It's actually all the energy levels of water. The water vapor molecule has a lot of different ways of rotating and vibrating. And that's why it's our Earth's actually biggest greenhouse gas. It has a lot of ways to absorb energy. Maybe there's the model. So this actually is supposed to help tell you what's in the model. If you sort of figure out which model fits the data better, it can help you learn what's in the model. And this particular planet, it's a big gas giant. It doesn't have liquid water, but it does have water vapor and methane in the atmosphere. So if we can't go there, why look? We can learn a lot about planets from remote observations, including details about what they're made of, what's in their atmosphere, and any biosignatures. So to summarize, I went through the 4 questions that I get asked most often. What could aliens see looking at Earth from afar? We talked about the pale blue dot that varies in brightness with time, that has a spectrum that shows water vapor, signs of liquid water. It has oxygen, biosignature gas, and many other things as well. When will we find another Earth? I gave you a complicated story that many of you were skeptical about how we can put a giant occulting screen in space and block out the 10 billion times brighter sun and look for Earths directly. That was complicated. That would take 10, 20, even maybe more years. But the part 2 story was we can find big Earths orbiting small stars, and if they go in front of that star, probably anytime in the next few years. Can we go there? Not for now. If we can't go there, why look? I gave you a few examples. And I want to finish by telling you something that's actually related to the exhibit that's back there that I encourage you all to go and take a look at. And that is what one of our real goals is in Exoplanets. And there have been a few times in history when astronomy has changed the way that we see the universe. One of the times was just longitude, figuring out where you are on the globe, Earth, based on the stars. Another time was the Copernican revolution, and that's what the exhibit is partly about. It talks about how people in the Western world believed that Earth was the very, very center of the entire universe, and that everything rotated around Earth. How self-centered can you get? And then Copernicus figured out that the sun was the center, and Earth and the planets revolved around the sun, but people still thought the sun was the center of the whole universe. Ultimately, people realized that the sun was just one of 100 billion stars orbiting our galaxy, and that our galaxy was one of upwards of 100 billion stars. And so what we're trying to do in Exoplanets is to go one step further and take our Earth away from being the very center of everything by finding planets like Earth and by finding planets with signs of life on them. What we'd really like to do is to be able to take our children or grandchildren or nieces or nephews out to a very, very dark sky. And in that dark site, to be able to take them and to point to a star and say, that star has a planet just like Earth. That's our whole goal, and that's the thought that I want to leave you with tonight. Thank you for your attention.
If you have a question, I'll come by with a microphone.
If we find an analog to Earth, how similar would that star have to be to our sun?
Okay.
Is that a way to narrow down the search?
Good question. The question is, can we narrow down the search for that Earth twin or Earth analog by looking for a star like the sun? And the first thought would be yes. And so traditionally in exoplanets, people have only focused on stars like the sun. The closer the better. But remember the graph I showed you with the planets everywhere? That's not proving to be true anymore. We think that planet formation is random. it's a random process, and that when one planet forms and gets so big, nothing else can form. And why that happens where it does is not totally understood. So it may not be the best way. It may not be a guaranteed way, but it's a good place to start.
What do we know about the movement of the stars? Do they follow regular patterns or what?
What do we know about the movement of the stars? Do they follow regular patterns? Like in our solar neighbor, when we look at the night sky, the stars that are very close appear to be going in all different directions. But if you look at stars and try to put things in a bigger picture, people see them rotating around the center of our galaxy.
This is to pick your brain. What would you and your colleagues have to find to be put under house arrest for the rest of your life?
That's a good question. What would we have to find to be put under house arrest? He's referring to Galileo, who had a really radical discovery. And what's really fascinating right now is that, let me tell you a story about that for a second. One of the very best, in my job I get to travel a lot to places like here, and I get to travel around the world, and in November I was inside the Vatican at a meeting that was kind of a scientific group that they used to kind of educate them, and they kind of wanted to know, when will we find aliens? It was a bit of a problem. But anyway, the story was, over there right now, they love Galileo. The people there were just talking about, they would just say great things about him. So right now, what's interesting is all the stuff I'm talking about, it's so great because it's all mainstream science now. And that actually you're not going to get under house arrest for. I mean, I think people would be very skeptical if you came up and said, look, I found a piece of a UFO, some kind of metal that just doesn't exist on Earth. I don't think you get under house arrest, but I think people would be quite skeptical about that, at the level that they were skeptical about Galileo.
You have a slide that shows the different sizes of planets that have been discovered. Does that kind of skew the thinking a little bit based on limits of detection? Like, if you had to answer the question, how many Earth-sized planets do you think there are relative to the Jupiter-sized planets? What sort of a guess might you make? And also, just real quick, in that picture, in that slide, there were some very low mass planets by some. I didn't remember what the method was that they were detected. I was just kind of curious about that method.
Yes, well, it was a question about the graph that about the planets that we know about, and the question was, it's a little misleading because I didn't say how many stars have planets. Let me say that about 15% of stars seem to have giant planets like Jupiter, where an Earth should be, or closer. That's very few, right? 15%. So maybe another 50% have Earths where they should be. So this figure was a little misleading. And the other question was, there's a few very low mass stars and low mass planets. Can you turn the lights down for a second? This is one Earth mass here, and there's some that are reaching down to Earth. But look how close they are to the star. Mercury's here. Mercury's this far. These planets are very low mass. They're probably 15 times closer to their star than Mercury is to our sun. And so it's actually easier to find planets close to the star. You can kind of see that by the way this graph is. So they're just easy to find. You can find low mass planets close to the star and close to very low mass stars, and that's what those planets are. So they're kind of the easiest ones to find right now.
And excuse me, sorry, one more. Just that timing method. What is that?
Oh, right, timing. Timing actually is, we tend to ignore those, that's why I didn't mention them. People who discover them don't get too happy either. But they're actually pulsar planets. They're around an old dead star called a pulsar, and these pulsars beam deadly radiation. And so it's a very precise, they're actually almost as precise as atomic clocks, because they're spinning rapidly every millisecond, and they're beaming right to us. And actually people timed that beam and showed that beaming actually changed, and they could show a repeat, and they could interpret planets going around the star. So it's incredibly sensitive. But right now they've looked at all the pulsars out there that they can do this measurement on, and people just tend to ignore them because it's a deadly environment, and they're so far away it's hard to do any follow-up studies on them. He was talking about this one here that's basically lower mass than Mercury.
Carl Sagan used a formula to figure out the probability of life on other planets. And over the years, has that probability increased? Or
That's a good question. And I think you're referring to the Drake equation, which actually is on, if you picked up one of the postcards, you'll see it listed there. Now, unfortunately, some of the letters in that equation we can't pin down right now. What has changed is the first 2 or 3 terms we actually can start to give you a number on. There's one term like how common are other Earths. In a few years from the Kepler Space Telescope, we can answer that. So we don't have enough information to answer that, to solve that, write down the answer to that equation yet. We're making progress on the first few terms.
What about broadcasting prime numbers and then looking for prime numbers returns?
That's a very detailed, that question opens a whole big can of worms. If you Google Stephen Hawking, you'll see, he was in the news last week because he said it would be so dangerous and crazy to beam anything, broadcasting to the aliens that we're here, because it's in the history of Earth, it's never been successful. If a more advanced civilization comes to you, they'll probably obliterate you. So we're not beaming. I think you can save that question for the next speaker who listens for signals from extraterrestrial life. But certainly, they're hoping that they can get a message with prime numbers or with some other kind of message that they can understand and solve the code. So that idea is certainly out there.
Compare light years with seconds.
Oh, compare light years with seconds. It's a kind of unfortunately, years is a bit of a misnomer because light years is really a distance. How far does it take light to travel in a year? So I can convert light years to distance for you. And 1 light year is about 6 trillion miles. So in 1 year, light can travel 6 trillion miles. And to put that in perspective, from our sun, it takes 8 minutes for light to get from our sun to us. So really, it's more of a distance thing than time.
For an M-type star, wouldn't the zone of habitability be extremely small?
The question is, for an M-type star, wouldn't the zone of habitability be extremely small? And do you mean small in area or just small in? Delta R. Delta R. Yeah, it's actually, there's no reason for it to be smaller in delta R than around a sun-like star. So, it's just some distance from the star where the outside of the planet could be the right temperature for liquid water. There's really no real reason why it should be shorter, but I'll elaborate on that and say we don't really know how big that habitable zone or that Goldilocks zone is. We have sort of conservative estimates. We're not sure really what it's like. It could be much bigger than we think.
One of the spectacular accomplishments in the space program was Cassini visiting a gaseous planet where they were as much interested in the moons as they were in the planet. And I'm wondering if we may be selling these gaseous planets short for places for life because they may have moons that can support life systems on them.
Absolutely. The question is, we may be selling the gas giants are exciting because they can tell us maybe there's a moon that has life. And the question about Titan, one of Saturn's moons, is one of the most interesting objects in our solar system. People think it is a place where all the ingredients for life are. And maybe that means there is some kind of life that can live in a different kind of liquid than water. Yes, and it's true that other planets can have moons. They'll be harder to detect